In this video, we'll be looking at some of the concepts that linear graphs share with other graphs, in particular quadratic graphs. So for a linear graph, the equation is y equals mx plus c, where m is the gradient and c is the y-intercept. So for the graph that I have here listed with its formula and also drawn, you can see that its gradient is going to be rise over run, which is 2 over 2, which is 1, and the gradient there is 1 times x, and the y-intercept is minus 2. So the gradient is 1, which is what m is, and the y-intercept is minus 2. All graphs have gradients. And of course, two important points for any graph, or two important values for any graph, is the x-intercept, or intercepts, and the y-intercept, or intercepts. So let's look at a quadratic. Here I have an equation, y equals x squared minus 5x plus 6. It's a quadratic graph because it's got an x squared. It also has an x term and a constant term. They don't stop it being a quadratic. It's the x squared that's the important part because it's the highest power of x that's in the equation. Now let's have a look. Here's the equation of the graph, and it goes down and follows this parabolic path. At either end, it's heading off to infinity. At this point here, it crosses the y-axis, so that's the y-intercept. It has two x-intercepts, one down here at 2 and another one at 3. So this quadratic graph, because it's squared, actually has two x-intercepts and one y-intercept. It also has a gradient. The gradient is constantly changing though. If I start here and walk along the graph, I go downhill, which means it's negative, and it's pretty steep, so it's a fairly high negative value. Then it starts to level out and becomes flat at the bottom. It's like a valley, isn't it? And then it increases in its gradient again as it goes back up again. So unlike linear graphs where the gradient stays the same, for a quadratic graph the gradient is continually changing. Here are three different quadratic graphs. They all have the same parabolic shape. So you can see the parabolic shape of a quadratic. But what's different here is, while a linear graph always has an x-intercept and a y-intercept, quadratic graphs don't have to have an x-intercept. In this example here, we've got a y-intercept and two x-intercepts. In this equation, for this equation here, the graph only has one intercept, and it's just touching, it's not really crossing, it's just meeting the point 0, 0. And in the third example, there are no x-intercepts. The graph doesn't go down far enough to hit the x-axis. There's a little bit more to quadratic graphs as well, because while these graphs all have a cup shape, as if they could hold a liquid, there are graphs that are upside down, and on the next slide we'll see that. So you can see here that if I have a negative in front of my x squared, like both of these graphs do, instead of being a cup shaped, the quadratic actually, its parabola is a hill shape. So it goes up to the top of the hill and back down again. And again, there doesn't always have to be an x-intercept. In this case here, there's a y-intercept but no x-intercepts. It never reaches up high enough to reach up to the x-axis. In the graph on the right, there are again two x-intercepts. So quadratics will always have a y-intercept when they're written in this form with y equals. They don't always have an x-intercept though. They can have 2, 1 or 0. All quadratics have continually changing gradients. When the equation has a negative in front of the x squared, we get the hill shape. So the gradient is positive along here. At this point here, right at the top of the hill, it's 0 gradient, it's perfectly flat. And as you come down, the gradient becomes negative and increases in a negative fashion, becomes more negative. For the equations where the x squared has a positive x squared, the reverse happens. You start off with a negative gradient, comes down to flatten off and become zero gradient, and then increases in its positivity again. When we measure the gradient of a quadratic, and to do this we use something called calculus, what we do is we put a tangent at any point. So at this point here, the gradient of this line that I've just drawn, which is a tangent at that point, is the gradient of the graph at that point. But as you can see, if I pick another point, say here, and do a tangent, the triangle will be different. And so the rise over the run will be different for both those triangles. And that sort of makes sense because you can see that the slope is different in those 2 points. To find the y-intercept of any graph, we do the same thing. We know that anywhere along the y-axis, which is anywhere along here, we haven't moved sideways. If we haven't moved sideways, that means x is 0. So anywhere along here, x must be 0. So what we do is we let x equal 0, or we set x to 0. So let's have a look at the first one. If I do y equals minus 0 squared minus 1, I'm going to get minus 1. And you can see from the graph that minus 1 is indeed the y-intercept. In the second equation, let's do the same thing. Let's make x equal 0. So we'll get y equals 0 squared minus 5 times 0 plus 6, which is 6. And you can see from the graph as well that 6 is actually the y-intercept. So similar to linear graphs where we had y equals mx plus c, for a quadratic, the constant on the end, in this case minus 1, and in this case plus 6, is the y-intercept. Because when you make the x's worth 0 in both equations, you only end up with the constant left. To find the x-intercept, we're going to set y equals to 0. So in the first equation, I'm going to get 0 equals x squared minus 5x plus 6. To find the answer, I need to factorise that. So I'm going to factorise it, and I'm going to get x minus 3 and x minus 2. Now the answer to that needs to be 0. To get 0, one of these two multiplied numbers, the x minus 3 in brackets, which is a number, and the x minus 2, which is a number, needs to be 0. That's called the null factor rule. So I'm going to start off and look at one of them separately. Let's just look at the x minus 3. So if x minus 3 was to equal 0, x would have to be 3. Looking at the other one, if x minus 2 happened to equal 0, then x would have to be 2. And there's my two answers, 2 and 3. And that's why there are two intercepts for x, because there are two potential answers that make 0 for y. In the second equation, there's a bit of a problem, because if you look at the equation and the graph, you'll notice that from the graph, the actual parabola doesn't cross the x-axis. So let's try that and see what happens. I make y equal to 0. So 0 equals minus x squared minus 1. To solve that, I need to get x by itself, so I'm going to add x squared to both sides. That gives me x squared equals minus 1. Then I need to square root both sides to find x, so x is actually equal to plus or minus the square root of minus 1. Now you can't square root minus 1. The answer is imaginary, and we deal with that in something called specialist maths. So when you get the square root of a negative number, what the maths is really telling you is there's no real answer. And we know there's no real answer because the graph doesn't cross the axis. But one day you'll find out there's an imaginary answer. So here's a couple for you to try. Just turn the video off for a minute, have a go at these, and then I'll do the answers shortly. So let's work these out. I'll make y equals 0. 0 equals x squared minus 7x plus 6. Need to factorise that, so what are the factors that go into 6 that make 7? Be minus 6 and minus 1, which means that x minus 6 can be equal to 0 using the null factor rule, or x minus 1 equals 0, so x equals 6, or x equals 1. And you can check those by substituting them back into here and seeing if you get 0 for y. I invite you to try that. For the next one, 0 will be equal to x squared minus 6x plus 9. So to factorise that, I need to make them both the same, so they'll need to be both x minus 3. And so therefore x is just equal to 3, or x is equal to 3. So we've got the same answer twice. Because we've got the same answer twice, that means that this graph just touches the x-axis once, whereas this graph cuts through twice. So now that you've worked that out, what I'd like you to do is actually draw those graphs, sketch them, and show your teacher. So just to finish off, here's a couple of other graphs that aren't quadratics, but also have intercepts. Let's have a look. This is, on the left, is a graph of y equals 5 times sine x, and you can see it has the shape of a wave. Another reason why sine is very important in maths. It has a highest value of 5, which corresponds with this number here, doesn't it? Let's have a look at the x-intercepts. There's one here, one here, one here, one here, one here, one here, one here. Seems to be quite a few. How many do you think there are in actual fact? There's one y-intercept. What about this other graph? Y equals 2 to the power x. This graph shows exponential growth. I can see there's a y-intercept here. What's the x-intercept, I wonder? See if you can work those two out and check it with your teacher.